Okay, so this is ionic bonding, right? It occurs between metals and non-metals. Electrons in the outer shell of the metal atom is transferred to the non-metal, right? So metals will lose electrons and will become positively charged ions, and non-metals will gain those electrons that were lost by the metal and will become negatively charged ions. Um, and an ion is an atom that has lost or gained electrons. Now, in this image below, I'm just going to zoom in for you. This is an example of ionic bonding in sodium chloride. We said sodium has one electron in its outermost shell, right? It's shown there, right there. That electron is the electron in sodium's outer shell because it's in group 1. So it has one valence electron. Chlorine has 7 valence electrons in its outermost shell because it's in group 7. Now, during ionic bonding, sodium, which is a metal, will lose its electron, and that electron will be transferred to chlorine, which is a non-metal, right? So metals lose electrons, non-metals gain electrons. And when sodium loses that one electron, it becomes positively charged and it becomes a sodium ion, right? So when metals lose the electrons, they become positively charged ions. Then for chlorine, chlorine gains that electron, and when nonmetals gain electrons, they become negatively charged ions, right? Remember, an electron is a negatively charged particle. So if sodium is losing an electron, it's losing a negatively charged particle. So it's becoming more positively charged. If chlorine is gaining an electron, chlorine is becoming more negatively charged because it's gaining a negatively charged particle. And so that's why it's forming a negative ion, right? Then it says ions produced by metals in group 1 and 2 and by non-metals in group 6 and 7 gain full outer shells of electrons. So they have the same electronic structure as noble gases in group 0. So remember I told you noble gases, group 8, they have we call them group 0 actually because they have a charge of 0, right? The last group in the periodic table. So we see here when that sodium lost that one electron, the outer shell was lost, and now the shell here has 8 electrons, so it has a full outer shell. The chlorine as well, when it gained that one electron, here it had 7 electrons, so it didn't have a full outer shell. Here, because it gained that one electron, it now has a full outer shell. So that is what they're talking about. They're talking about the fact that the outer shells in both these ions are full, and noble gases have full outer shells, right? Then it says electron transfer during the formation of an ionic compound can be represented by a dot and cross diagram, and that is what this is below. This is a dot and cross diagram of ionic bonding between sodium chloride, which is a ionic compound, right? Any questions?
I think I'm gonna have to listen to the recording.
That's fine. You can do that. And then let me know if you still don't understand. We can also go through more examples of different ionic compounds, right? Let's move on to covalent bonding. Oh, here's a joint ionic structure. Okay. Remember I said that sodium chloride is not made up of just one sodium and chlorine atom, right? It's made up of hundreds or millions, sometimes, probably hundreds or thousands of sodium chloride, sodium and chloride atoms. So think of the green balls as sodium and think of the blue little balls or dots as chlorine, right? So a joint structure of ions is formed by some compounds that undergo ionic bonding, where they have where they have hundreds or thousands of sodium and chlorine atoms, and that is what makes up the sodium chloride compounds, the ionic compounds such as sodium chloride. So the reason we draw sodium chloride like this on top is just so that we are able to understand the type of bonding that's occurring in chemistry. But the actual compound would look something like this, right? It's held together by strong electrostatic forces of attraction between oppositely charged ions. And since the structure is three-dimensional, the forces act in all directions, right? So, for example, sodium chloride, which is a table salt, or it's also called NaCl, right? It's the small blue dots. Okay, they said think of the small blue dots as sodium and the large green ones as chlorine. So let's change that. Blue dots are sodium and green dots are chlorine. So this sodium chloride compound would look like this in real life if we were to draw it. Okay, any questions?
No.
Okay, so if they ask you about the bonding between ionic compounds, they have strong electrostatic forces, and that is why they have a high melting point, because it requires a lot of heat in order to break those strong forces between these compounds. And those forces act in all directions. So imagine how strong those forces must be. Then we go to covalent bonding. Covalent bonding is when atoms share one or more pair of electrons, right? So small molecules such as hydrochloric acid, hydrogen, oxygen, chlorine, ammonia, um, and so on have strong covalent bonds within their molecules. So in covalent bonding, you'll notice these are all non-metals. So they on the right-hand side of the periodic table, right? Because covalent bonding only occurs in non-metals. And polymers are large covalently bonded molecules. So polymers are basically repeating units of the same element, right? So, for example, two oxygen molecules bond together to form O2, which is oxygen gas. And so we say they form a polymer. It's just basically repeating units, right? So, giant covalent structures are called macromolecules because they consist of many atoms covalently bonded in a lattice structure. So remember when we did sodium chloride, we said it has a giant lattice structure. A covalent bonding will be the same. It will also have a giant lattice three-dimensional structure, but it will have repeating units. So it will have the oxygen molecules bonded to each other, and then they will be also those double bonds will also be bonded to each other, but they will be bonded together in pairs like this as well, right? And so the giant covalent structure consists of many atoms covalently bonded in a lattice structure. Examples of these are diamond and silicon dioxide. Diamond has repeating units of carbon-carbon bonds that are bonded closely to each other, but in the structure as well, they bonded to each other. And the diagrams to show these substances could be dot and cross diagrams, and they will show repeating units of these polymers using a single line to represent a single bond, and ball and sticks. Let me see if I can get a structure of diamond for you so you can see what I'm talking about, because I don't feel like my diagram is doing justice. Um, Covalent bond. Okay, Got it? I just need to share my screen with you now. There we go. Okay, confirm when you can see my screen.
I can.
Okay, so here we have the structure of graphite, right? And let me just see if I can. In graphite, each carbon atoms forms three covalent bonds with three other carbon atoms. So we can see there's three atoms bonded together here, and then another three, and they form bonds with each other, right? Um, and then there's weak intermolecular forces of attraction between these bonds. And that is one of the properties of covalent compounds. Covalent compounds have weak intermolecular forces, and that's why they have low boiling points, right? Because it's easier for heat energy or heat to break those forces because they are weak. And we see here graphite, we said the main structure of graphite is those three carbon molecules bonded with um, a single carbon. And they carbon will have one unpaired electron that will bond with another carbon atom, the electron of another carbon atom. And they will form pairs. Initially, they would have been unpaired. When they bond with other carbon atoms, they form pairs, right? So this is an example of a large structure that is formed by covalent bonding. Let's go back. Okay. Let's go down to metallic bonding. Okay, so the bonding of metals consists of positive ions, and positive ions, remember, are atoms that have lost electrons, right? And delocalized electrons arranged in a regular shape. Now I'm gonna zoom into the bottom here. So this is metallic bonding. We have the positively charged metal ions. Those are the red ones. Those are the gray ones. The metal ions, right? They have positive charges. Then we have the red ones, which are the electrons. And the thing that happens here is these metal ions share those electrons between them, and that is how um, metallic bonding occurs. And those positively charged those negatively charged electrons, they float around those positively charged ions, and they don't have any specific space. They're all over. So we call them delocalized electrons because they, as you can see here, they don't have a specific location. They can occur anywhere. And so we call it a sea of delocalized electrons because there's so many electrons around these positively charged ions. So the delocalized electron system consists of electrons lost from the atom to form positive ions, right? And then delocalized electrons are free to move throughout the structure, and they interact with those metal ions to form metallic bonding. The delocalized electrons are shared throughout the structure, so metallic bonds are strong, right? So metallic bonding is the bonding between positively charged ions and delocalized electrons in a lattice structure, right? Any questions regarding that?
No.
Okay. So that was the last thing here. I think we have about 5 minutes. Let's just go back to the original document that I was showing you, right? Of questions. Um, There we go. Okay, let's go to question 12. It says, what is a delocalized electron? So we just discussed this. How would you define a delocalized electron?
What does define mean?
How would you describe it?
Can you remind me what the delocalized means?
Delocalized means it doesn't have any specific location in the structure. It can be anywhere.
I can't remember.
Okay, so remember this is metallic bonding. It's between positively charged ions and delocalized electrons, right? So those electrons are free to move throughout the structure. So remember, let me draw this for you again, like it was in that diagram. We had those little gray balls, and those were the positively charged ions, right? Then we had those little red dots, and those were the delocalized electrons. So delocalized electrons are electrons that are free to move. They are free to move throughout the structure, this metallic structure, and they interact with those positively charged ions, and they're shared among those ions, and that forms the metallic bonding. Okay, so metallic bonding is between metal is occurs in metals only. It occurs due to the metal ions interacting with the delocalized electrons. So delocalized electrons are electrons that are free to move through a metallic structure. Any questions?
So, can you repeat again?
Okay. So in metallic bonding, right, we
Yeah.
have positively charged metal ions, and we have electrons that are free to move throughout the structure, right? And metallic bonding occurs when these delocalized electrons basically they so, okay, they are attracted, the metal ions, right? The metal ions are positively charged, we know that, and then the electrons are negatively charged, right? So those metal ions, they attract those electrons, right? And that is what metallic bonding is. It's it's when those valence electrons, these are valence electrons, right? They are they don't have any specific location. They are free to move around the metal structure. Can you see that?
Yeah.
Right. So they interact, they can be shared between these metal ions, and they will have an electric charge. Remember, they're negatively charged, so they are charged particles. So they are going to be shared between these metal ions, and they will have a charge, and then that will cause bonding, right? Remember, it looks more like this. The electrons get stuck. Sometimes they'll move and they'll go to another ion. And so they have a charge. They have a negative charge. The ion has a positive charge. And so they will form by the interaction between the metal ions and those electrons is what causes metallic bonding, right? Then it says, explain why metals are good conductors of electricity, right? So remember, I said the electrons rather carry a charge, right? And so
Yeah.
that charge allows electricity and heat to travel through the metal. And because of that, metals are able to conduct electricity. The electrons carry the charge.